You cannot use anything. Just your pen or pencil and my exam papers. And if you have a question about the exam, I will give you time about like some minutes. I cannot decide because I don't know how many you have. These are the questions, 20 questions. In other words, even before coming to school, you know the exam. And please browse and ask questions shortly. Yes?
So we could, make sure I'm clear, but we could write down formulas or explain it?
Right. The shorter the better. But what I don't accept is this one. Oh, it's used for integration. Of course, it's used for integration, but I don't accept that kind of thing. But other than that, mostly short answers are okay.
So we could, like, for the example, that number 7 there, we could just kind of write down.
You can even sketch those. You can draw something like a trapezoid. You can draw, or
Are all 20 questions going to be on there, or is it just going to be?
it's actually this one. Only difference is the spacing. Spacing will change.
So all 20, if we know all 20 are going to be on there, you're not going to pick 10 of the 20? Or
Just everything. Because in the past I gave like, I guess 30 problem set, and I asked 10. Students gambled. They didn't study all 30. They studied 10. Their 10 was different from actual problem, and they complained. He's unfair. So I decided to ask everything instead of letting you gamble. Then let's resume. So we already know how to find the area of the flat case. It's a rectangle. This means always thin, so I don't even want to mention this one more time. Just a thin case, right? So thin area this way, or thin area this way. But now the next task is a little bit more theoretical. That is the area like this or the other way, right? It could be given differently. This could be given the other way, right? So how to determine the thin area of this shape? That is the next thing that I will mention. And it all comes from calculus. So let's do it. To determine a parabola, we need 3 points. We need 3 points. So we should know at least 3 points that we can determine. How do we determine 3 points? We usually determine the 3 points this way. So let's reverse it. There is a function and there is an interval. There is function and an interval. And we pick 3 points this way. This point, right? This point, this 3 point, and then we find the vertical height, right? We find the vertical height. So we find this point, we find vertical height here, we find the vertical. So we choose these 3 points. Once 3 points are chosen this way, then we can create the parabola passing through these 3 points. So we choose a parabola passing through these points, these 3 points, and then after finding the parabola passing through these 3 points, we find the area under this parabola, right? Of course, I can stretch these things all the way down. So this is the key idea. And in fact, this is the homework part 2. I ask you to practice calculus one more time to really find the value. But roughly, how do we find these things? So we break up the thin interval, a to a plus 0.1, right? We break up this interval one more time. In other words, we need to calculate this thing, a plus 0.05, right? So we should break up one more time. In in second order function, we break up twice. In third order function, we break up 3 times. In fourth order function, we break up 4 times. Spin universe is broken up that many times. Right? This thin piece is broken up 1 time. Yeah, total twice, right? Total twice, I mean. There are total 3 points. Do you follow me? Then after breaking up, we integrate this function. We integrate the function from a to a plus 0.01, and then ax squared plus bx plus c is done, right? Then we now determine the area. And what people did was the calculation, and also you will be asked to calculate this thing, and the calculation led us to the formula like this. This thin piece distance is called h, right? This is called h. So what is h? In this calculation, what is h? 0.05 is h, right? So that h over 3 times f of a plus 4 times f of a plus 0.05 plus f of a plus 0.1. So this is the formula. Of course, the detailed formula exists. You don't have to write down the formula itself because the detailed formula is here. And this is found by Simpson. So this is called the Simpson's rule. So the formula exists right here, right? So please browse the explanation and ask questions. If you don't, then I will mention about the next case. About the next case will be enough. I gave you the formula so that you can use this summary under any circumstances. Someone may ask you to use fourth order function to determine. In any case, this is the formula to calculate thin piece, right? This thin piece. Then the next thin piece is from a plus 0.1 to a plus 0.2, but we should break up this one more time here, right? So a plus 0.15 is necessary in the next piece, and the next piece. And so we add these pieces together to determine the area. Any questions? So when you do homework, you are asked to do this integration. So roughly the idea is, doing a integral of this thing, 1/3 x cubed, right? And so, right? And then using a, b, c, we can determine this things completely. So this is homework. So I assign this. So Simpson's method is explained. Then the next method is this. I will use new column instead of this. The next method is using, instead of parabola, so I will make it bigger. Even though it's a very thin piece, I will intentionally make this bigger. So this is a bigger piece. A, and this point is a plus 0.1, right? The same thickness, but I intentionally magnify the piece. Then the next method is breaking this up more. Breaking this up more. So total 3 times, right? So 3 subuniverses, right? 3 evenly divided subuniverses. And this point is a plus 0.1 over 3, right? A plus 0.2 over 3, right? 0.3 over 3. So these are used. Then we can determine 4 different heights. We can determine the height here. We can determine height here, and height, right? So we can determine this heights. So we can determine the height at A, height at this, and heights at these points. Then we can find the function passing through these 4 points. We can determine the third order function, cubic function, passing through these 4 points. Then we are integrating the third order function from A to A plus 0.1, and then third order function looks like this. Of course, we can determine these A, B, C, D. We can determine these A, B, C, D by using the point information. There are 4 points. There are 4 unknowns. Then 4 unknowns can be determined by 4-point information, right? 4 unknowns, 4 equations. This first order 4 unknown system, right? First order 4 unknown system. So by doing this calculation, we can do the integral, and some people did it, and the result is this. Assume that h is this, right? Assume that h is this. H is this, and then h equals 0.1 over 3, right? H is this. Then with this h, it is 3 times h over 8, and then f of a plus, as you can see here, 3, 3, 1 is used here. The 3 f of a plus 0.1 over 3, and then 3 times f of a 0.2 over 3, and then f of a plus 0.1 over 1, right? Or 0.1. So this is the thin piece that you can calculate using 3/8 rule. 3/8 rule, right? 3/8 rule. So we are using higher order function to integrate instead of lower order functions. So any questions? So we can continue, right? Essentially, theoretically, we can continue all the... Assume that someone gives you $1 million. Then, would you go to the 100th order? If someone gives you $1 million, would you go to 100th order function or not? Definitely, right? So, it's possible to do it, right? It's possible to do it. But let's stop the theory part, and I will explain about some practical part, unless you have questions. So let's use our computer to really do the integration. So you may pick up 2 random points. So you may pick 2 random points determining the interval. What to what do you want to integrate? What to what?
-1.
-1 to what?
To 1.
Yes, -1 to 1 was chosen. So we want to integrate the function from -1 to 1. Right? We want to integrate the function from -1 to 1. And the function could be, for instance, x cubed plus 3x minus 5. Minus 5 is not great. I don't want to use big numbers. -1 might be okay. So this is a function we want to integrate. Then I will break this up by very thin piece. In my opinion, this is it. So I will break this up by thin pieces. So I will break up this by these 2 thin pieces. I say this is thin. Then you may pick any method. Do you want to see one method? First method or like midpoint rule, anything I will do. So pick your method. What method do you want to see?
I heard Simpsons.
Great, Simpson's method. Then let's use Simpson's method. To do it, I should break this up into 3 equally divided parts, right? And then I should do the same thing to the second piece. So let's focus on the first piece. Then I need to calculate the height at this point, height at this point, height at this point, height at this point, and so on. So we need these heights. So now I will use computer to do the calculation. Oh, it blocks it. So I will pause and then use computer. But before using the computer, I will write down the result. The area equals the first area, right? First area plus the second area. And the first area equals by Simpson's rule, h over 3, and then first height, and then 4 times second. This is not 1. Height represents height. And then, so these are heights, not ones. These are heights. Then let's really calculate the numbers. H is 0.5, right? H is 0.5. And the first height is when x is negative 1. When x is negative 1, negative 1, negative 1 plugged in gives us negative 5. Plus, so I will indicate we are not handling numbers by using this. It doesn't represent the number, it represents heights. And then 4 times the next height. 4 times the next height is at the negative. So because of this reason, it's a good idea to make a function. So f function is x cubed minus, plus 3 times x minus 1. Right? This is a function. Then f of negative 1 is 5, negative 5, right? F of negative 0.5 equals this one, right? 4 times (2.625), right? And then f of 0. F of 0 is obvious, right? F of 0 is 1, right? Negative 1, obvious. Plus negative 1. So this determines the first height, right? First area, including the negative area. If it goes down, it's negative area. Any questions? The next piece will be calculated soon. The next piece equals h over 3, the first height plus 4 times the second middle height and right side height. And we calculate these things. 0.5 over 3, and then negative 1, 4 times f of 0.5. F of 0.5 equals this one, right? So we use the number 0.625 plus now f of 1. F of 1, 3. Then essentially we are done, right? By adding these things, we can find the area. So let's find the area. So you don't even have to program it. So as I mentioned, someone couldn't program before, so gave me a solution like this. I accept the solution. Plus 0.5 over 3, multiplied by minus 1 plus 4 times 0.625 plus 3. Do we need more parentheses? I think these are enough. So negative 2 is the answer. Negative 2 is the area. Simpson's rule gave me negative 2. So after this, I got the area negative 2. Then let's do the calculation using calculus. Using calculus. Do you know how to integrate in MATLAB? Do you know how to do it? INT? F of x from x to
I think we just put the numbers
minus 1 to 1. Will this work?
No, you have to say sims first.
And then?
That's a symbolic integration. I think you want to do trap.
Sims xf.
Just x.
You don't want symbolic integration. You want integration from that.
So what should I do? Let me know the answer. Then I will use maple. Maple, help me. So I will use maple. Oh, maple has disappeared. Then I will use my hand calculation. I studied very hard when I was a high school student, so I can do this calculation. Please let me know the problem when I go to the new page. So we are doing the calculation of this area from minus 1 to 1. And what is the function? I forgot the function. What is the function?
Plus 3x.
And then?
Minus 1.
Great. Then this is odd function. Odd function from negative 1 to 1 becomes 0. Odd function from negative 1 to 1 is 0. And then this one integrated. Then it is minus 1 from negative 1 to 1. Then it is negative 1 multiplied by 1 minus negative 1. Negative 2. Exactly. Amazing, right? Simpson's rule is amazing, right? Amazing. So we chose only 4 points, but it worked. So any questions? So we are integrating the function, not by doing these things, but by Simpson's method, or some method. So if you have questions, ask me. Yes?
For homework, would you be giving us something like that where we can double check our approximations with something like that if we wanted to round out?
Because I give the same problem, you can check one time on top, and then use that to check all other answers against it. There is only one problem. Then you can use the one problem, and then check whether your answer is close to the solution. The answer is pi over 2, I guess. Pi is 3.14. Pi over 2 is like 1.56 and so on. You are meaning the homework, right? So, I'm just asking this problem.
Just saying, like, yeah, I get it.
Yeah. So I already gave the solution. You should get pi over some number close to pi over 2. Pi over 2 is about 1.56 and so on, right? So let's do the calculation using MATLAB. Pi over 2. Like you should get around the number around these things in your integration. Then the other things are very similar and so on. So in fact, we can do these things for general order function, right? Using the general order function, we can do it, right? for any by using any general order function, we can derive the formula. But very soon, not very soon, maybe sometime later, you will see the reason why this increment isn't necessarily good. This increment isn't necessarily good. Sometimes about Simpson or 3/8 might be enough. Going over that might be too extreme. In addition, there might be unexpected some malfunction because of some theoretical reason. So these kind of approaches called generally Newton-Cotes method. So Newton-Cotes developed these kind of directions. Of course, some names were attached, such as Simpson, right? So this direction is complete, and if you have a question up to this Newton-Cotes idea, ask me. If you don't, then I will briefly show you one aspect that I didn't clearly mention, but wrote down in the summary. When you do the integration, we usually need h, right? Sometimes full h, sometimes partial h. In any case, we need h when you do the integration. Then, what kind of h gives us the best result? That is the question, right? H should be very small or large h is okay, something like that. So to do it, people did the analysis and got this kind of result. So I will focus on this part. Assume that we use the zeroth order method or midpoint rule. The error is this way. In other words, if you want to get like millionth digit accuracy, your h should be 1/1000 or lower to get 1/millionth accuracy, right? So 1/1000 is necessary. But if you use, for instance, this method, your h can be 1/10. Do you follow me? So depending on method, you may need to use rough h instead of very refined h. And take a look at Simpson's method. This is the second order method, Simpson's method. It achieves this thing. It's amazing. So if you use 1/100, it is better than over 1/100 million, right? The accuracy is great. So because of this reason, as I mentioned, people mostly stop at Simpson's method. Because if you use refinement like 1/100, then it will be very close to the actual solution. Take a look. Very strangely, the 3/8 method isn't that great compared to our effort, right? It was harder to apply 3/8 method, but it wasn't very great. But suddenly the next method goes up, right? Jumps up. But if we go to this level, some bad phenomenon happens. In any case, you can consider these things in the future, not now. Then the next approach is this one. Assume that you are integrating a function given in a large interval, not just small interval, large, like from here to Boston. You are integrating something from here to Boston. Then what is the best way? Use this Maclaurin summation formula derived from number theory. So I don't derive it or even explain, just give you the formula. To integrate it from here to Boston, you break up each mile, and then at each mile you calculate the height, right? And then add these things. And at the end we have, right? You take average. then that will be very close to the solution, and that is adjusted by this strange factor coming from number theory. This B2K are called Bernoulli number that has some table. So just giving you the possible approach when you study like earth science, right, or something, then you need to integrate over a huge interval. Then you can use this kind of approach. So I gave you a few things like this. How to determine Bernoulli numbers. Usually coming from this. So in this sense, a Newton quote direction is done. Then I will cover the same topic in completely different method in the next topic. Questions? Then let's do it. It's very inconvenient to break up and then add these in pieces, right? It's very difficult to do these things all the time and slow. Assume that you are fighting. You are a pilot, and then you are fighting, and you are checking the possible location of the enemy. But your computer relies on these things, and integral results should be used. While you are calculating, they may already shoot you, right? So you need a faster approach doing the calculation. So the next idea is this. We want to do the integral from, for instance, a to b, f of x dx. But instead of really doing this kind of thing, is there a method like this? Oh, I just want to multiply some value. I just used this letter, but I don't want to intimidate you, so I will use just a box, a number times f of some number, right? And then number times f of another number. So can I do these things a few times? Like first 2 times, 3 times, or 4 times, 5 times? Because addition is not very difficult, right? Then your airplane, your fighter may add these things fast and then defend or attack, right? So is there the approach like this? And the answer is yes, there is an approach like this. So instead of doing the breakup, adding and stuff, just calculating f at some sample points, right? At some sample points with appropriate weights, add, and then this addition may be close enough to the integral. Then you do the integral very fast and then do the next step. Do you understand the idea behind this approach? And Gauss developed this idea. And the answer is yes. So theoretically this is it. Assume that we have a function, then we can represent this by using just one number times f of one number. It's possible to do it. Of course, I'm not saying this is accurate. I'm saying this represents the integral close enough. But one number is not better than two numbers, right? So we may do this thing. So I will use the first approach. Second approach is we may do these things with two numbers instead of one number. Two numbers might be better than just one number, right? Then this may better approach the result, better approximate the result. And the third one is using three numbers instead of just two numbers. And generally, we can use, for instance, n numbers. We can use n numbers to do the calculation. Then, what is the similarity and the difference? Similarity is this. We are adding. Difference is this. We are not really doing the explicit calculation. We are just adding at some specific points. That's the difference. In other words, Upstairs, we evenly divide the interval. We evenly divide the interval. Here, we pick these points randomly. Randomly is not a good word. Strategically. We pick these points strategically. That's the difference. So for instance, if we choose one number, I will go to the next page. Oh, no, not the next column might be now. So I will reshape the problem from -1 to 1. Strategically, I chose this thing. Then, if I just use one number, what will represent it? The number that I can strategically choose is 0, f of 0. And then what number should I multiply to? So this will represent the integral. Amazing, right? So with this, I can somehow approximate the integral. In other words, if I use this kind of machine, then I can react very fast. But one number cannot be better than two numbers. So assume that I use two numbers. I don't memorize the second number, so I will read the note and then write down the two number representation. If I use two numbers, then strategically I can use these things. So this is the one. This 1 over square root of 3 chopped. 1 over square root of 3 truncated. So strategically I chose these two numbers to represent the integral. If I use three numbers, then the integral. So after this I will not write down the left side. I will just write down the right hand side. The strategically chosen number is this. So this is the one that approximates this is the function that approximates the integral. In other words, it's very cool stuff. You're asked to integrate, you don't even consider doing integration, right? You don't even consider doing integration. You just add a few numbers and then say the answer. Amazing, very close, right? So let's really do the things using MATLAB, because my calculation skill isn't very good. So I will use the MATLAB. So I will program this thing. So f function, I cannot program. Can you program it? So I will do the calculation. Take a look. The previous f integral was -2. I just chose three numbers and did it. And take a look. It's already very close. Amazing, right? Compared to the effort that we had made before, it is very close, right?
Those numbers work for any function.
For any function. So, good point. So let's make up. The problem is just, we don't know how to integrate using MATLAB.
You could use the help tool.
I see. Help, and then menu? Help.
Help, and no, go to help at the top.
Help.
Type integrate here.
I don't need symbolic result, I want numeric result, numerical result.
That's the symbolic toolbox. So type integrate all the way out. So polynomial probably uses a polynomial to approximate.
Mm-hmm.
I think it's quad type
Yeah.
right there. I think it's help.
Uh-huh. And then quad,
Yeah, type help right there.
here, right here.
Right here, help, and then space quad. All on the same line.
I see. Will this work, right? From 0 to right? But instead of worrying about it, let's try to open Maple one more time. Maple one more time. We failed. Then let's use known function, such as cosine function. So cosine x from minus 1 to 1 is equal to sine x from minus 1 to 1, then sine 1 minus sine negative 1. Sine negative 1 is minus sine 1, so 2 times sine 1. I can do sine 1 at least. At least I can do it. So 2 times sine 1. How can I return back to the workspace?
You start typing.
Slow now. Why is it so slow? Did I do something? So let's do the calculation one more time. So I will get this result. I will do the integral of cosine function. I do not know why it hangs here. Strange, right? Now, thank you. So we now have this one. So f will be defined. F is a function. F is a function cosine x, right? Cosine x is f. And now I will calculate this thing, right? This thing with f. This is the result that I can get from the 3 value usage, right? I use 3 values. Now I will do the exact result multiplied by this, right? Take a look. I chose 3 points and did the integral and compare the actual result, right? And the 3-point result. They are close. So isn't it amazing? So this was developed by Gauss. So instead of really doing any calculation, we evaluate the value or height of the function, right? Value of the function strategically, and then add the result. This is called Gaussian quadrature method. Then you may wonder about the number of points that we can do. And you can do as many points you want, right? 1 point is okay. 2 points are okay. As you saw, 3 points are very good. 4 points are okay. And as you can see, I made a table. How to read the table? This is the way you read the table. 1 point, right? Then you should have the node point 0. In other words, f of what? 0 should be calculated. Of course, we are doing the integral. This table is made for the integral from negative 1 to 1. This table is made for negative 1 to 1. Later I will let you know the way to vary this interval. But right now we are focusing on this. So I will return back to the problem itself. So we are doing the integral from negative 1 to 1. And then we are doing this thing. So this is the node. This is the weight, right? So I call this node and weight. So first node position and the first weight are all tabled. So let's go down. So first node point is 0, first weight is 2. And what about the next one? Next node point is this, right? Or exact point is this one. And next weight is this one. And if you use 3 nodes, here and weight is here. And here and weight is here. Oh, I don't find the next one, right? You need 3 points. And usually we use symmetry. 0 is symmetric to itself. What about this one? Negative 0.77 can be used, right? Negative 0.77 this point, and the weight is the same weight is used. Do you follow me? So I just wrote the half portion. The other half uses symmetry. But if we use 4 points, then this one and negative this one, right? With weight here. And this one and negative of this one and weight. So we pick 4 points. So we do this. So this is the idea of Gaussian quadrature. So I will pause and then you may browse the idea and ask questions. If you don't that, I will let you know how to derive these things in the first place and other changes or possible improvements. So Gaussian quadrature is covered here. And if you have a question, ask me. So Gaussian quadrature is completely different from Newton-Cotes integration. Newton-Cotes integration is the actual breakup and then calculation and adding the steps. Gaussian quadrature is choosing strategic points and then add at strategic points. No questions? Then the one that you may be asked to do, it might require 7 points. So I asked you to really integrate a function and use Gaussian quadrature with 7 strategic points, right? 7 strategic. So one line program will do it. You don't even need program, just one line command will do it. After defining the function f, right? What is it? What is the command? This number times f of 0.0 plus, right? This number times f of this one plus f of minus this one. Then already 3 points, right? And then this number times f of this one, right? Plus f of minus this one. Then already 5 points. And this number times f of this plus f of minus this. Of course, parentheses inside the parentheses because we use the same. That means essentially by doing it, you solve one problem. By just one command, will solve the problem. And then you can compare the result with the actual integral, that is pi over 2, that is 1.57. You can compare. So we are almost done with this thing in actual sense, in practical sense, but I will cover the other aspect of this thing. For instance, how to derive these kind of things in the first place, or how to generalize this kind of idea, or what about different interval? Instead of negative 1 to 1, I assume that I want to 2, then what should I do? That kind will be mentioned. But understanding this is very essential. Questions? Then let's cover one thing at a time. So I will follow my notes. So one more time overview or review. By a sum at strategic points, we approximate the integral. So we don't do any real integral stuff or area adding stuff. We just choose strategic point and do the addition. That's it. And here, these are predetermined. As you can see, did I change it to makeup or did I already give you these things before the semester. I gave you these things, not just me, somebody, Gauss already calculated these things before. Then we just use any f and then use this formula. So we use predefined points and ways to determine the integral. Then the next thing is a to b. Gauss did a nice thing, but it doesn't help me. My integral is from 2 to 5. Gauss did it for -1 to 1. My integral is 2 to 5. So he doesn't help me at all. No, he can help you. How? Just by simple rescaling, right? Simple rescaling. By doing simple rescaling, from -1 to 1 becomes from A to B, right? So, from -1 to 1, x varies from -1 to 1, then t varies from A to B, right? T varies from A to B if x varies from -1 to 1. In other words, initially, problem is given in A to B form, but you can convert the problem into -1 to 1 problem. It's very straightforward. So I will show you how I did it. First of all, x varies from -1 to 1. T varies from A to B. So assume that x is -1, what happens? Assume that x is -1, what happens here? -1, then minus b plus a. And minus are cancelled out. There are two a's. So what do you get? If x is -1, what do you get? A. If x is 1, what happens? B. So -1 becomes A, 1 becomes B. So interval is handled. Then because of this change of variable, we should use the chain rule, right? We should use, so dt and dx are calculated, right? dt and dx are calculated. So the problem is given this way in the form of dt. But dt is, because of this reason, what if we differentiate, then this b minus a over 2 times dx, right? So we should replace dt by this one. And t here is also replaced by this one. Just change a variable. Then you can extract this part and then rewrite the function using, instead of g, we call the whole function f. Then suddenly we have f function. Then you can apply the Gaussian quadrature. So no matter what, you can apply the Gaussian quadrature. I mean finite interval, not infinite interval. So you can do these things, but now I ask you to really let me know the answer. So do this thing. I want to do 1 to 5. So I want you to do 1 to 5. Then write down the correct form to practice. In other words, to apply Gaussian quadrature, how to convert this problem? How should you convert this problem? Please let me know the result. With if you need the formula, I will show you the formula. So I asked this part, and you should arrive at this part, and let me know what f is. G is like sine t. Did I give sine t? G is sine t. Then what is f of x? Did you get this result? In other words, if you put this back in, then 2 is written here, and this one. So f function is 2 times sine of this thing. This is f function. Right? Did you get it or not? If you didn't, then let me know. Then, let's integrate this function. Let's integrate this function using our, so f of x now equals 2 times sine 3 plus 2 times x, right? This is the f of x function. Then let's do the Gaussian quadrature to do it. So the calculation gave us 0.2574, right? This is what I get. So I will write it. Let's do it. And now I will use my hand calculation to do the integral. So I will do the hand calculation. Negative cosine t is the integral of this thing from 1 to 5, right? Then negative cosine 5 minus negative cosine 1. So it is minus cosine 5 plus cosine 1, right? So by just pure hand calculation, I got this thing. So let's do the cosine 1 minus cosine 5. Cosine of 1 minus cosine of 5. So Gaussian quadrature applied for different intervals. So you can apply the Gaussian quadrature even though you have different intervals instead of just negative 1 to 1. Then the next part is, because we have about 20 more minutes, I will mention about the approach to find it, and then after doing it I will mention about the differentiation. How can you find it? So for instance, assume that we have 1 point, right? How can you find W1 and X1? 1 point, I will show you, and you can use this method to solve some problem. The idea is this: I will use simple function such as this. Assume that f of x is 1. Then I can plug in 1 here in the place of f, right? Then what can you get? Minus 1 to 1, 1 dx equals w1 times 1, right? Because do you follow me or not? I replace f of x by 1. Simplest function. Simplest non-trivial function is 1. Then the integral here gives us 2, right? The integral here gives us 2 and w. So I could calculate w1. Right? Now, the simplest one is used. Right? Simplest one is used. So, I will use the second simplest one. That is f of x equals x. Right? This is the second simplest one that I can use. So, let's use it. Then, the left side is negative 1 to 1 x dx, and the right hand side is w and then x1, right? Because f of x is x, x1 is x1. And w1 is already found. Right? And if you do the integral of this left side, it's 0. This is 0, right? This integral is 0. So x1 is 0 from this. And people did this kind of calculation theoretically and derived those tables. And can you do the same thing on other situations? And the answer is yes. So, for instance, assume that we are asked to find the Gaussian quadrature like this from, for instance, 1 to infinity with 1 point. Then what is W1 and X1? These W and X are different. And because we are not doing the same thing, right? We are not doing negative 1 to 1. We are doing 1 to then first thing you should do is what? F of x should be equal to what? Identically equal to 1, right? Then 1 to infinity, 1 log x dx equals w1 times 1, right? Because it's exactly. Then you can calculate w1 by doing this integration, right? This is not a calculus course, so I want to do integral. You should do integral. And the next one, how can you find next one? Use what? Use this, right? So this is homework. You should do these things at home, right? And then determine next one. Second step is f of x equals x, call this x, and then use these things in the position f, right? In the position f. So 1 to infinity, x log x dx equals x w1 times x1, right? And w is already found here, then some number, right? And then you can determine x1, and then determine. So you can do this. So theoretically, you can find these kind of things in various functions. There are other functions. You assume that you have e to the negative x multiplied in front, then you can do the similar thing. But essentially the same idea over and over again. Then the final approach is this. The final approach is this. We are doing the integral. So integral in positive sense is the area, right? So we are doing the integral, and the integral in positive sense is this. So someone consider this idea. Oh, let's make a box. General enough box containing the domain, right? So we create the box. So box area can be calculated, right? How can you calculate the area of a box? Size, length times, right? This length, right? So we can multiply two sides to determine the area. Do you follow me? Then the next thing is this. We just randomly shoot several points. So I will see this thing, I will see you, and then randomly. Then check whether the point belongs to the integral part or up in the air. I dot how many points? For instance, I dot, let's say about 12 points, right? And how many dots are below? 5, right? So 5 among 12 is below, right? Then, then because of this, area should be close to 5/12 of the box size. And this method has a name. It's called Monte Carlo method. So this city is famous for gambling, right? So you don't rely on this method. You don't rely on this method. But this is the crux of this method. In other words, you randomly generate the points inside the box and throw those points, and then check how many points landed at the integral area. And then count those, and then compare the ratio. And then ratio multiplied by the box gives you the area. So very, very unreliable method. But people use it, especially finance. They want to invest in stock market, and they need to do something, and they are using these things. So if you don't have a question, this can be applied in two-dimensional case. Assume that you are applying in two-dimensional case. Then, instead of just rectangle, you are using real three-dimensional box, right? Inside the three-dimensional box, you create a volume, right? Create the volume, box volume. Then box volume, among box volume, something is under, something is over. You count the number of points under. So that's the approach. Then finally, brief coverage of differentiation. I didn't cover very many things in differentiation, so I will just go through the notes. I explained this This is a summary of Monte Carlo method. Here, percentage of dots, right? Multiplied by area. It's this simple. Finally, differentiation, and essentially differentiation means the derivative, how to handle derivative, how to handle first derivative, second derivative, and so on. Why do we care about these things? Because not in this chapter, but in chapter 8, ordinary differential equation or some other course called scientific computation needs these kind of derivatives. So how to differentiate the function? Usually we use this notation. Instead of using f of xk, we just shorten it, right? Subscript k. So f of xi plus 1 means, this means f of point x sub I plus 1, right? So that value minus the previous point over h determines the derivative, right? Generally. So this is it. So we forwarded one step and then did the difference and then divide by h to find the derivative. Do you follow me? It's pure definition of the derivative. Without limit, right? With the limit we do the derivative definition, but without limit we do it. Then this is forward. What about the central one? We forward one step, we backward one step. That means the distance is not h, distance is 2h, right? Instead of going just forward or backward, we are going this way, then the distance is 2h. So we are dividing by distance between the two. So this is central approach. What about the second order derivative? Second order derivative is done this way. So this kind of approach exists. So in other words, once you see the second order derivative, how to do it? You don't really differentiate, but you calculate the values at some points, right? And evenly divide the points, and then do the evaluation of the value, and then using this value with the, so it's very similar to the finite difference that I showed you, f bracket 1 to 3. You did the calculation. It's very similar. Any questions about this one-dimensional finite difference formulae? So we can do this kind of calculation. And second order is two-dimensional derivative is possible. Then partial derivative. So this means we do the partial derivative with respect to x or y. So x direction we advance, right? Forward, right? And we use forward in y direction, or we do the central thing in x direction, y direction. And sometimes we have the irregular boundary. In other words, we cannot sometimes evenly divide the interval. If we evenly divide the interval, the distance is usually h, right? But sometimes it is not h. Then the distance is used to do that. So roughly, these are used in this course. So I somehow covered the steps. But if you have questions or difficulties, ask me. And if you don't, then you may leave the room. And next time, you need to take the exam. But during the week, you may email me if you have questions or even come to my office to ask questions.